Hi guys, welcome back to the channel. So, we've all heard about Apple's new M1 chip, and Apple promised a lot with this chip. They promised a 3.5 faster CPU, as well as 3.9 times faster video processing, all while using only 25% of the energy that a standard Mac would that didn't have the M1 chip. These were bold claims from Apple, and the world has been poised to see how effective these M1 chips really are. And now we're starting to get the first real-world tests of just how quick they are. So, how fast are they? They're fast. They're really fast. Over at MaxTech, the team tested an $899 Mac Mini versus a $2,500 iMac, and they got some shocking results. The M1 Mac chip absolutely blew the Intel-driven iMac out of the water. So we now know the M1 chip is living up to Apple's claims. But what is making the M1 chip so much faster than computers with more RAM and larger GPUs? So in order to understand why the M1 chip is so fast, we first need to understand what a CPU, or central processing unit, is. A CPU, also called a microprocessor, pulls in instructions from memory and then performs those instructions in a sequence. Trying to boil a CPU down to its basic form, it's essentially a number of named memory cells called registers and a number of computational units called arithmetic logic units, or ALUs. The ALUs perform the arithmetic operations within the CPU, like addition, subtraction, etc. But the ALUs cannot do this without the data to manipulate, and this is where the registers come in. The ALUs are attached to the registers, and it is the registers that pull the data from the computer's memory. So, as an example, say we are asking the CPU to add together the numbers 10 and 20. First, the CPU needs to load the numbers from random access memory, or RAM, and store these numbers in a register. So here we are grabbing the number 10 from memory location 140 and storing it in the register R1. We then do the same for accessing the number 20 that's stored at memory location 180 and store this in the register R2. Only now can the CPU use the add operation of the ALU to perform the operation on these numbers. But how is the M1 chip faster? Well, firstly, and importantly, the M1 chip is not a CPU. Usually, a computer has multiple different chips, each with a particular job. These chips often need to work together to perform certain tasks. The M1 chip groups all of these chips into one silicon package. The M1 chip does have a CPU, but it also contains the computer's GPU, memory, and much more, meaning the chip makes up the whole processing needs of the computer. In the industry, this is known as a system on a chip. For years, CPUs have been made better by simply adding more general-purpose CPUs. These are otherwise known as cores. The more cores a computer has, the more powerful its processing ability. However, in recent years, Apple has begun to maneuver away from this architecture. Rather than having multiple general-purpose CPUs, they're producing more specialized chips that are very good at doing particular tasks. These chips are able to perform their allotted tasks much faster and for much less energy than a general-purpose CPU, drastically increasing the chip's performance per watt. The M1 chip includes multiple of these specialized units. Now, although I've said the M1 chip is not a central processing unit, it does have a central processing unit within it. This is in charge of running most of the code involving the operating system and its applications. However, it also has a graphics processing unit, or GPU, which handles graphics-related tasks such as visualizing an app's user interface and 2D, 3D gaming. In addition to this, it's got several other components though. It has an image processing unit, or ISP, which is one of these specialized units I've spoken about. The ISP drastically increases the image processing capabilities of the M1 chip, and that's why its processing of imagery is so much faster than the industry standard. It's also got a digital signal processor, which handles more mathematically intensive functions than a CPU, including decompressing music files and things like that. In addition to this, a neural processing unit used in higher-end smartphones to accelerate machine learning AI tasks, but it's also being used more commonly in computers as well. These include things like voice recognition and camera processing. It also has a video encoder and decoder, which handles powerful, efficient conversion of video files to different formats, as well as a secure enclave, which handles encryption, authentication, and security. And finally, a unified memory system, which allows the CPU, GPU, and other cores to quickly exchange information. That last point, the unified memory, is one of the key ingredients to why the M1 chip performs so well. But it's a little bit of a difficult concept to get your head around. Cheaper computers tend to have integrated CPUs and GPUs, often referred to as integrated graphics. These are infamously slow, and this is largely due to the way each of them ingest data. In order for this system to work, the memory needs to be partitioned, meaning the CPU and GPU uses its own memory and cannot take data from each other's. Therefore, if the CPU wants to use the GPU to process something that's stored in the CPU's memory, then rather than just handing the GPU the data, the CPU needs to copy the data into the GPU's memory, a process which is exceptionally slow. This is because each unit likes to ingest data differently. A CPU wants to receive the data very quickly, and they're happy to ingest the data in very small sizes, whereas GPUs are the opposite. They don't need the data to be delivered quickly, but when it is delivered, it wants a lot of it. Because of this, putting a GPU on a CPU is usually not a good idea, because you dramatically decrease the potential of the GPU by starving it of the data it craves to work effectively. Apple has tried to address the fallbacks of shared memory using its unified memory architecture. There is no special area reserved for just the CPU or just the GPU. Memory is allocated to both processors. They can both use the same memory. No copying is needed. Apple uses memory which serves both large chunks of data and serves it fast. In computer speak, this is called low latency and high throughput. Thus, the need to be connected to two separate partitions of memory is removed. The M1 chip also uses an ARM instruction set. These classically produce less heat, allowing the GPU to have a higher heat budget than a GPU that was placed on the same silicon die. This is unlike AMD's and Intel's architecture that uses an x86 instruction set. ARM and x86 are a little bit outside the scope for this video, but if you want to know more, let me know in the comments and I'll do a separate video on it. I'll also include a link in the description if you want to know more now. This architecture is part of the reason, but not the whole reason, why the M1 chips are so fast. In addition to these advantages, the general purpose CPU that's already in the M1 Mac chip, called Firestorm, is in itself really fast. In order to make a general purpose CPU faster, you need to do one of two things. You can either make them perform more operations in a sequence faster, or you can make them perform tasks in parallel, meaning they are able to perform multiple tasks at once. The Firestorm CPU in the M1 chip makes use of the latter of these two, by increasing the parallel processing capabilities of the chip. In developer speak, parallel processing is more commonly known as threading code. However, writing functional threaded code is some of the most difficult code to write, and so it requires a very talented programmer to be able to write it. Most developers are not able to write an effective parallel code. And therefore, if you want your product to be both very fast using parallel processing, but also accessible to most developers, you need to produce a system that takes care of the parallel processing for you, without having to have a programmer write advanced threaded code. To achieve this, the M1 Firestorm CPU uses something called out-of-order execution. Out-of-order execution is a complicated topic, and I'll be honest, it took me a while to get my head around it. Using out-of-order execution, developers don't need to thread their code to get the same advantages. From the developer's point of view, each core is just running faster. In order to understand this, we need to look back at how a CPU works. Asking for data at a particular location in the computer's memory is a slow process, but a CPU is capable of getting multiple bytes of data at the same time from a location, meaning that getting 1 byte of information at memory location 150 is no quicker than getting that byte and the subsequent 9 bytes of information in memory. In other words, getting 10 bytes of adjacent memory is no slower than getting just 1 byte, as long as this information is stored adjacent to one another. This means your microprocessor can get a whole chunk of information at once, with instructions to carry out on that data. But when you write code, you write it in a sequence, so that actions happen in a particular order. This is where out-of-order execution comes in. A modern CPU uses out-of-order execution to analyze what operations rely on what data. By doing this, the CPU knows which operations can be performed simultaneously, as well as those that need to be performed sequentially. I think this is best explained with an example. Here we can see a short buffer of instructions a CPU might receive. First, let me explain what this syntax means. The first part is the action being performed. So in operation 1, we can see that the action is multiplication. The second is the register location to store the result of the operation. So in operation 1, that is R0. The following parts are the register locations to perform the operation on. So in operation 1, we have a multiplication being performed on R1 and R2, and the result of this operation should be stored in the register R0. Now, multiplication is a slow computing process, but because the addition in operation 2 requires the result of the multiplication in operation 1, then this operation cannot be performed until the operation 1 has taken place. It will just have to wait. However, operation 3 doesn't rely on any of the outputs of operation 1 or 2, meaning it is independent of these operations, and can therefore be performed in parallel to operation 1 without waiting for that operation to complete. This is how out-of-order execution works, but in real life, the CPU would be performing this on hundreds of instructions. This produces a parallel execution of the code, without the developer having to write complicated threaded code themselves. With that being said, a developer should always write threaded code if it's within their competency and it makes sense to do so. But when combined with out-of-order execution, we can get some incredible results, as we're already seeing with the M1 chip. But you might be asking, why is the M1 chip necessarily better at out-of-order execution than the AMD and Intel chips? Well, the speed and effectiveness of out-of-order execution all comes down to how quickly you can fill up a buffer of micro-operations. The more micro-operations there are in your buffer, the higher the probability that the CPU will be able to find multiple operations that it can do in parallel. The speed with which a computer can refill this buffer with micro-operations depends on how quickly the computer can chop up a program's machine code into micro-operations. This is done using something called a decoder. This is where the M1 chip has a massive advantage. Even the meatiest of Intel's and AMD's microprocessors only have 4 decoders. The M1 chip has 8. This means it can fill up the instruction buffer faster than any of its rivals. In addition to this, the M1 chip also has an instruction buffer that's 3 times larger than the industry standard. So not only can it fill the instruction buffer quicker than its AMD and Intel rivals, but it also has more space there to fill. So why can't AMD and Intel just start building chips to compete with the M1? Surely they can just add some more decoders or create some more system-on-a-chip solutions. Well, it's not actually as easy as that, for 2 reasons. The models of companies like AMD and Intel rely on them producing general-purpose CPUs that people can just slot into a PC motherboard. However, things are starting to move away from this design to a more system-on-a-chip architecture. This means that rather than obtaining physical components from vendors, you now have to obtain the IP rights to use this particular design from vendors, meaning you buy the rights to the design of a CPU, GPU, I/O controller, etc., and then you use that to make your chip using something like a foundry. Now here's the problem. Intel, AMD, Nvidia, they're not going to start licensing their IP to computer companies like HP and Dell. You could argue that companies like Intel might just start making their own system-on-a-chip solutions. But to what specs? Different computer companies often provide different advantages to their clients, and that's possible because they assemble the different hardware in their computer's motherboard. It's not going to be economical for Intel or AMD to supply individual SoCs to each of their clients, so they're in a bit of a catch-22 scenario. For Apple, of course, this isn't a problem. Now that they've pivoted away from Intel, they control every piece of the pie and can build their own chips to match whatever specifications they choose. The second reason that AMD and Intel are at a disadvantage is because of the instruction set they use in their chips. As already mentioned, the M1 chip uses the ARM instruction set, whereas Intel and AMD tend to use the x86 instruction set. Now, as I've already said, the inner workings of these instruction sets are beyond the scope of this video, but there is an important difference that we need to consider. In an x86 instruction set, the instruction can be anywhere between 1 and 15 bytes long. In the ARM instruction set, the instructions have a fixed length of 4 bytes long. Why is this relevant? Well, if we go back to our concept of decoding, you're probably wondering why Intel and AMD can't just put more decoders in their CPUs. They can't do this because of the amount of work required to split up each stream of bytes into instructions within a decoder. If these instructions are all the same length, as they are in the M1 chips, then this is an incredibly simple computing task to perform. However, as the x86 instructions can be different lengths, the decoder cannot tell where an instruction starts. It has to analyze each individual instruction to calculate how long the instruction is. Currently, AMD and Intel chips just attempt to force this solution by decoding the instruction from every possible start point, meaning there are a lot of possible wrong guesses. This adds such complexity to the decoding stage of this process that adding extra decoders is almost impossible. In fact, it is so difficult that AMD has admitted that 4 decoders are likely the upper limit possible for their chips. All of this puts AMD and Intel at quite a disadvantage, and if they're going to keep up with the latest M1 chip, they're going to have to be quite inventive with the way they design their chips. This also affects the PC market. It's kind of the first time that the Apple products have become cost effective compared to a PC, considering how much better the processing power is now. Thanks for watching, guys. I'll be really interested to know what your thoughts are, so please leave them in the comments below and I'll try and reply to everyone. If you enjoyed this video, consider subscribing to get all my content. And as always, happy deving, guys, and I'll see you in the next video.